Today, we're opening up a 4,500-year-old cold case. We're going to try to reverse engineer one of the absolute greatest construction mysteries in human history. We're not just looking at the Egyptian pyramids as ancient tombs. No, we're looking at them as massive, mind-bending engineering puzzles. All right, let's just dive right into it. Picture this. 4,500 years ago, zero pulleys, no wheels, no iron tools whatsoever. Yet the ancient Egyptians somehow leveled an entire plateau down to a fraction of an inch to build literal mountains out of stone. How on earth did they pull that off? People have been arguing about this for centuries. So today, we're strictly sticking to the archaeological record and modern engineering studies to see how raw human ingenuity made this happen. To piece this puzzle together, we'll start by busting some ancient myths, then check out how they actually cut the stones, figure out how they moved them, dive into the Great Ramp debate, and finally, look at the sheer manpower it took. All right, part 1, myths of the pyramids and debunking ancient misdirection. So, we've got to clear up a massive misconception right out of the gate. This whole idea started way back with ancient Greek historians like Diodorus Siculus, who claimed 360,000 men were constantly slaving away. For centuries, the popular myth has been that the pyramids were built by slave labor. But archaeology tells a completely different story. Back in 1990, they actually excavated the workers' cemeteries, and it turns out these monuments were built by tens of thousands of highly skilled, paid workers. They lived in dedicated camps. Some worked for a direct salary, while others did it as a form of tax payment, called corvée labor, during the flood season when they literally couldn't farm anyway. These workers were highly organized, well-fed, and actually highly respected. Moving right along to part 2, cutting the stones and the tools of the trade. Okay, before you can even build a pyramid, you need the rock, right? Mostly limestone from Tora and massive granite blocks from Aswan. But here's the kicker. They didn't have steel. They didn't even have iron. They had to rely on arsenical copper for their chisels and saws to cut the softer limestone. But what about that super hard granite for the burial chambers? Copper won't even leave a scratch on that stuff. Their solution? Sand. Yeah, sand abrasion. They'd use copper saws but pour quartz or corundum sand right into the groove. The sand actually did the cutting, not the copper. And for the absolute hardest stones, they literally just pounded the rock away using heavy, hard, round stones called dolerite. Just pounding, hour after hour. I mean, talk about backbreaking work. But here is the craziest part of all that. Despite using nothing but copper, dolerite, and sand, the results were absolutely flawless. When modern civil engineers, like Dr. Craig Smith, evaluated the site, they were blown away. He pointed out that the precision of these ancient builders actually rivals 20th century laser leveling. Think about that. They leveled a 13.1-acre base to within a fraction of an inch. Using basic tools and trenches filled with water to find a level line, I mean, their accuracy is just astonishing. So you've cut these massive stones to laser precision. Now what? That brings us to part 3, moving mountains and the logistics of transport. How do you move those stones across the Egyptian desert? Well, we have this massive visual clue from a 12th dynasty tomb belonging to a guy named Jehuti-Hotep. There is this illustration on the wall showing 172 men pulling a giant alabaster statue. And the estimated weight of that single statue? 60 tons. 60! So we know for a fact they were more than capable of moving impossibly heavy singular weights using just human draw teams. But the real secret sauce here? Water. Remember, they didn't use wheels. Instead, they loaded these massive stones onto wooden sledges. And if you look closely at that tomb illustration, there's a guy standing at the front pouring water onto the sand right ahead of the runners. It totally changes the friction dynamics. Wetting the sand makes it slick and firm, which stops the sledge from digging in. It's a simple trick, but it allowed surprisingly small teams to pull an immense amount of weight. Now, how did the stones get to the Giza Plateau in the first place? Well, we just got some breaking evidence on this. A satellite study from May 2024 actually mapped out the Auramont branch. This was a 64-kilometer extinct waterway of the Nile, about half a kilometer wide, that flowed right up to the Giza construction sites. It eventually dried up due to drought, but back then, boats could just deliver the materials directly to the base of the pyramids. And we actually have the diary of an ancient official named Mer confirming this exact thing, detailing how they transported the limestone blocks by boat. Okay. So delivering the stones to the base is one thing. Hoisting them up a 400-foot monument, that's another. Welcome to part 4, the ramp problem and reaching the peak. This right here is why Egyptologists are still endlessly debating today. There is no single perfect answer. A massive straight external ramp? Basically impossible. It would take more material than the pyramid itself and leaves absolutely zero archaeological trace. What about a zigzag or spiral ramp? Well, they use way less material, but they'd wrap around the edges and completely block the builder's line of sight. And you need that line of sight for the exact geometric leveling we talked about earlier. Then there's the internal ramp idea. Brilliant in theory because it explains the lack of external ruins, but, it remains really tough to definitively prove. But speaking of internal ramps, architect Jean-Pierre Hundin came up with this truly fascinating hybrid approach. He hypothesizes that they built the first 30% of the pyramid with a standard external ramp. Then, they completely dismantled that ramp, took those stones, and used them to build the rest of the way up from the inside using an internal spiraling ramp. When they got to the corners, they'd have these 10-square-meter open notches with a simple wooden crane just to rotate the blocks and keep moving them up. Fun fact, back in 1986, a researcher actually spotted a desert fox high up in a notch on the Great Pyramid, which kind of makes you wonder, is there a hidden internal pathway used to climb up there? Tools, transport, ramps, check. Now for our final puzzle piece, Part 5, the pyramid workforce in manpower and scale. To really wrap your head around the scale of the manpower we're talking about, just remember this one number, 2.3 million. That is the approximate number of individual stone blocks in the Great Pyramid alone. Most of those core blocks weigh around 1.5 tons, and the massive granite roof beams for the king's chamber, up to 80 tons each. It is just staggering. So, how many people did this take? Well, using critical path analysis, which is the exact same math we use to plan modern skyscrapers today, a construction management study estimated a peak workforce of about 40,000 people. And these folks were incredibly organized. Based on the tombs of the supervisors, we know the workforce was split into two main crews of 2,000, then subdivided into named gangs of 1,000. Those were split again into groups of 200, and finally down to highly specialized task groups of about 20 workers, every single person knowing their exact job. But here, right here, is where the logistics get totally mind-bending. To finish the Great Pyramid in the generally accepted timeframe of a couple of decades, this massive workforce had to be placing roughly 180 blocks every single hour. Do the math on that. During a 10-hour workday, they were setting 3 blocks into their final positions every single minute, 1 block every 20 seconds. Sound impossible without modern machinery? Let's check out the hard proof in Part 6, the climax, and modern experiments in pyramid building. Yeah, we don't even have to guess about this because we've actually tested it. Back in 1992, Egyptologist Mark Lenner and stonemason Roger Hopkins ran this awesome pyramid building experiment for TV. Using only ancient techniques, a tiny crew, just 12 quarrymen and 44 builders, managed to erect a small pyramid of 186 stones in just 3 weeks. Each stone weighed 2.2 tons. Most importantly, they completely proved that using those wooden sledges on lubricated tracks, a small gang of 12 to 20 guys could easily tow a 2-ton stone. The math literally scales up perfectly. So what's the big takeaway from this explainer? It's that the Egyptian pyramids absolutely were not built by magic. No lost technology, no aliens. No way. They stand today as a 4,500-year-old testament to unprecedented human logistics, flawless organization, and just absolute sheer ingenuity. This diagram compares the volume of a modern skyscraper to the Great Pyramid. Constructing this required stacking over 2 million stone blocks, some weighing as much as 80 tons, into a single precise geometric form. Because this scale is difficult to reconcile with a society operating 4,500 years ago, it created a vacuum in the historical record. When physical evidence for the construction methods wasn't immediately obvious, theories involving levitation, lost high technology, or alien intervention filled the gap. This lack of data also allowed for the persistence of the idea that the pyramids were built by a massive army of forced slave labor, a narrative popularized by Greek historians centuries after the fact, and later cemented by Hollywood. Attributing the construction to magic or forced labor oversimplifies the actual challenge. It replaces the complex reality of ancient engineering with a simpler, less interesting explanation. Modern archaeology has identified the workforce as a highly organized group of tens of thousands of skilled Egyptian citizens who were paid for their labor. Evidence for this exists in the ruins of the workers' village at Giza, shown here. The excavations revealed bakeries, breweries, and a cemetery with dignified burials, indicating a permanent, well-supported settlement rather than a temporary slave camp.
The project was managed through a structured hierarchy. A core group of 5,000 permanent specialists lived on site, while a larger force of laborers arrived in rotating shifts for their tax obligations. These men were organized into specific gangs and subdivided based on skills. Coordinating a workforce of this size without iron tools or the wheel required a system of supply chain logistics and mechanical engineering we are still working to fully map. The first stage involved quarrying millions of tons of limestone and granite. In the Old Kingdom, this was accomplished using only Bronze Age tools. This is an example of the technology available to the builders, an axe head made of arsenical copper. By alloying copper with arsenic and hammering the metal, the Egyptians created tools hard enough to work the softer limestone bedrock. For harder stones like granite, the builders used sand abrasion. They moved copper saws across the stone while feeding quartz sand into the cut. The sand acted as a grinding agent, allowing softer metal to wear through the harder rock. Once extracted, the challenge shifted to transport. While core limestone was quarried on site, massive granite beams had to be moved from miles away. This map shows the path of the recently discovered Aramat branch of the Nile. Now extinct, this waterway once flowed directly past the pyramid sites, allowing boats to carry heavy stone from distant quarries to the base of the construction site. For the land journey, workers dragged the massive stones on wooden sledges. By pouring water onto the sand in front of the sledge, they reduced friction by 50%, allowing teams to move multi-ton blocks. River navigation and the physics of sand friction explain how the materials reached Giza, leaving the question of how these stones were lifted into a shrinking vertical space. This is the central debate: how to lift 2-ton blocks hundreds of feet into the air, as the working area at the top of the pyramid becomes smaller with every layer. This diagram illustrates why a single straight ramp is unlikely. To maintain an incline that men could climb while pulling a sledge, the ramp would have to be over 1 mile long. Building it would require more material than the pyramid itself. Other theories suggest an exterior spiral ramp, potentially supplemented by levers at the corners. However, this creates a major geometric problem. An exterior ramp obscures the precise sightlines the architects needed to measure the corners, ensuring the pyramid reached a single perfect point. Jean-Pierre Houdin's internal ramp hypothesis suggests the pyramid was built from the inside out, using a spiraling tunnel. When blocks reached open notches at the corners, they were pivoted 90 degrees and fed into the next upward ramp, allowing teams to continue climbing. While theories like Houdin's have been tested with modern software, we have yet to find physical proof that definitively confirms one specific lifting method. The search for a single lifting method assumes the Egyptians used a static process. It is more likely they adapted their techniques as the structure grew, using different combinations of ramps and levers as the space became more constrained. This was not a society that arrived at a perfect architectural formula immediately. Their history shows a clear progression of trial, error, and mid-project correction. The bent pyramid is a physical record of this adaptation. Halfway through construction, the original angle proved too steep for the internal chambers to support. This image shows where the builders were forced to change the slope mid-construction to prevent a total structural collapse. This messy, iterative reality contradicts the desire for a clean, mechanical explanation. It suggests an engineering culture that solved problems through direct observation and on-site adjustment. The Great Pyramid stands today as a result of tens of thousands of people refining their methods through failure and iterative problem-solving, achieving a level of precision that remains visible across millions of tons of stone.